Thank you for the invitation. So thanks, Emmanuel, and also Sylvain for hosting my stay. It's always a real pleasure to come to Paris and to the ENS. So in my presentation today, I want to introduce you to the subject of exceptional points. And in particular, I want to try to convince you why they are actually exceptional, these special points. So let me just invest one formal slide into some definitions of what I actually mean when I call something an exceptional point. And in the rest of my talk, I want to illustrate sort of what interesting physics is entailed in those special non-Hermitian singularities. So an exceptional point is a special property of a non-Hermitian complex matrix or operator. And non-Hermitian is really essential here. So if you have a Hermitian Hamiltonian, for instance, like in quantum mechanics, without gain or loss, then you don't get this. At the exceptional point, this operator or matrix becomes defective. It means that you cannot diagonalize this matrix anymore, but you need a Jordan normal form to do this. That's the best you can do. And what's special and what's also different, what distinguishes an exceptional point from a conventional Hermitian degeneracy is that not only the eigenvalues of this matrix, at least two of them, become identical at the exceptional point. And since it's a non-Hermitian matrix, the eigenvalues are complex. And when they become identical, it really means that both their real and their imaginary parts become the same. But also, the corresponding eigenstates become completely parallel at this exceptional point. So in a conventional Hermitian degeneracy, you can always find a suitable basis in this degenerate subspace that is orthogonal. But at the exceptional point, those eigenstates become completely parallel. And that's actually the reason why the matrix becomes defective. So let me give you now a simple physical example of where you could find such an exceptional point and how you could study it. Well, the simplest possible case is a system described by a 2x2 matrix. And if you have a look, you'll immediately see that this is a non-Hermitian matrix that could, for example, describe two resonant modes in two circular optical resonators. But it could also be a 2x2 matrix that describes a system that's actually well studied here at the ENS, an atom in a cavity. And of course, both the modes and the atom and the mode in the cavity, they have a decay rate and a resonance frequency, which are described by the real and the imaginary parts of those diagonal elements. And the off-diagonal elements are, of course, the coupling between them. So what would you now have to do to reach an exceptional point? Typically, you have to vary two parameters. In this case of the two cavities, this could be, for example, this parameter A1 and G, which would be determined by, for example, the radius of this one disk, which would determine the resonance frequency of this mode. And G, the coupling strength, would be determined by the distance between those two resonators. So if you have those two parameters available, you can change them. Then the statement is you can reach an exceptional point. So how would you then see that you have an exceptional point? Well, you would just look at the eigenvalues of this simple 2x2 matrix and plot them. And since it's a 2x2 matrix, you have two eigenvalues. And since it's a non-Hermitian problem, those eigenvalues have a real part, which is plotted here, and an imaginary part that is plotted here. And if you vary those two parameters, R and D, which is the radius here and the distance, then those eigenvalues would change in their real and imaginary parts. And changing the parameters, you will get two eigenvalue surfaces that have this very beautiful prototypical structure that is unique to an exceptional point. And this structure shows you that if I plot those Riemann sheets, then in the real part, they will have an avoided crossing on one side and a crossing on the other side. And in the imaginary part, it's exactly opposite. You would have a crossing here and an anti-crossing here. And of course, there's only one point in this plot where both the real parts are the same and the imaginary parts coincide. And this is the exceptional point, which is right at the center of this Riemann sheet structure. So what would be a physical interpretation then of those eigenvalue surfaces? Well, the real parts of the eigenvalues would be something like resonance frequencies in your system. And the imaginary parts would be something like the widths of resonances. And apparently, around the exceptional point, you would then have something like avoided crossings or crossings of resonances, and also avoided crossings or crossings of widths of resonances. And at the exceptional point, at least two resonances would coincide both in their position and in their widths. So maybe you will ask yourself, isn't this something that I've seen already? And I'm pretty sure that you have. For example, if you go to this system that I was mentioning before, when you have an atom, for example, resonant with a cavity mode, and the two are really on resonance, then this would correspond, for example, to a position here, where sort of the frequencies are the same. This would be a cut through this Riemann surface, where you would see in the real part sort of resonance splitting originating at the exceptional point. And also, if you do the same cut in the imaginary part, you would see this here. Now, I plot this in a slightly different way to make this even more intuitive. I don't plot the real parts and the imaginary parts separately, but I plot them in one combined plot. So where the real part is on this axis and the imaginary part is on this axis, then you will immediately see that in this case of the cavity in the atom being on resonance, then this line here would be sort of the weak coupling limit of your atom with the cavity. And of course, this branch here would be the strong coupling limit, where you would get two polaritonic peaks. The difference between the two peaks would be the vacuum-Rabi splitting. And the exceptional point sits exactly at the transition between weak and strong coupling. So if I would vary, for example, one parameter here along the line shown here, this parameter, then I would go with my eigenvalues from weak to strong coupling. Yep.
Sorry for the naive question, but if the Hamiltonian is not a mission, the evolution is not unitary, so you lose probabilities. So
absolutely.
Could you explain what goes on?
Yeah.
Where are they lost?
Well, in this case of the cavity is open, so something leaks out. So it means that if you have a photon or field inside there, the field will slowly decay out of your system. So this is something that is intrinsic to this type of physics, that either you need gain that provides additional energy and blows up things that are in there, or you have leakage, or you have a combination of both. Only if you have gain and or loss, you will see this type of physics. Yeah? But of course, understand that in reality, a non-Hermitian Hamiltonian arises only when you consider just a subpart of the entire reality. It's not a closed system, exactly. Yeah. Another interesting connection that I want to make, which some of you may have heard of, is that if I choose this 2x2 matrix in a special symmetric way, in particular parity time symmetric way, where parity time symmetric way means that if I take this Hamiltonian, this non-Hermitian Hamiltonian, and I make a parity and time transformation with it, so parity would mean I exchange this element with this element, and time would mean gain becomes loss and loss becomes gain. Then Hamiltonian where those two decay rates are identical, or sorry, one has an equal amount of gain as the other one has an amount of loss, then I would have a parity time symmetric Hamiltonian. And for this Hamiltonian, this pitchfork diagram would look like this, which has the special form that before the exceptional point, the eigenvalues are on the real axis, which is somehow counterintuitive because you have a non-Hermitian Hamiltonian, but still it gives you real eigenvalues. That's the special feature of parity time symmetry. Only if the gain and loss is too strong, then you'll have a phase transition, and the eigenvalues will meet in the exceptional point and then branch off to the upper and to the lower part of the complex plane, but still maintaining sort of a symmetry that the value of gain is equal to the amount of loss. And sort of in a parity time symmetric system, due to the additional symmetry that you have, it's typically sufficient to just vary one parameter, like the gamma or the G, to reach the exceptional point. In a generally non-Hermitian system without the symmetry, you need to vary two parameters to get there. But those parity time symmetric systems have been studied a lot recently and caused a lot of excitement. There are lots of experiments. And let me just mention a few of them because they will also be relevant in the later part of the talk. So how would you realize such a parity time symmetric system in the lab? For example, you could take two waveguides, one with gain and one with an equal amount of loss. The coupling is due to the mode coupling between the waveguides that are very nearby. And if the gain and loss is weak, then you would be in this unbroken PT phase, how people call it. This is the phase where the eigenvalues are real, although you have gain and loss. And in this phase, independent of whether you inject the light in one waveguide or in the other, you will get oscillations back and forth between the two waveguides. This would be something like an equivalent of Rabi oscillations in such a parity time symmetric system. However, once you pass the exceptional point and you're in the PT broken phase, then what happens is that one eigenvalue will be have a positive imaginary part and the other one a negative one. And this corresponds to the case that if you inject light in the gain waveguide, it will stay there and be exponentially amplified. If you inject it in the loss waveguide, it will be attenuated. But there's a little bit of coupling between the waveguides such that this little bit that leaks into the gain waveguide will then continue propagating there and also be exponentially amplified. And this was nicely observed in this paper here 7 years ago. Already a little earlier, there was another experiment that I would like to mention where people coupled two waveguides with each other that didn't have this exact parity time symmetry, but a passive parity time symmetry, such that by making an appropriate transformation, you could map this system onto that. That's the basic story. But what they found there is also very interesting. You have two waveguides, one with loss and one with no loss, and they injected waves into the waveguide without loss, and then measured at the output how much of the injected flux would be transmitted totally through both waveguides. And what they observed was that if they increased the loss in the lossy waveguide a little bit, then the transmission would go down. That's what you expect. You add loss, something gets absorbed, you get less transmission. But then, if you crank up the loss even further, the transmission goes back up. And by adding more loss, the transmission is increased. So you get loss-induced transmission. And of course, as you can guess, the point where sort of this regime, the intuitive regime, is separated from the counterintuitive regime, that's again the exceptional point here at the center. And the reason why I'm mentioning this is because for us in Vienna, this was the starting point to think about this problem. And we were asking ourselves whether we couldn't see such an exceptional point and the associated behavior also in a laser. Yes?
Sorry to be so conventional, but accustomed to Hermitian Hamiltonian.
Yeah.
In order to, if I make a measurement, I must know what is the state. And the states are the right eigenstate of the Hamiltonian or the left one? They are not the same.
Exactly right. In a non-Hermitian Hamiltonian, the left and the right eigenvectors are not anymore the same.
Which one is the state?
Here I'm not even.
I want to make a measurement.
Here I'm not even talking about the state. This is a classical system. I inject. This is not a quantum state that I inject, but I inject a classical light wave that's described by a Maxwell equation, and I just measure what's the transmitted intensity of this wave in the end. Yeah. But of course, you're absolutely right that if you go to the quantum optics domain, not only do you have to ask yourself exactly what is your state, but also due to the presence of gain and loss, you will have to introduce Langevin noise terms to make sure that the commutations relations are intact. Then the fluctuation dissipation theorem comes into the game. You will get additional factors. What I'm talking about here is sort of the semi-classical limit where at the beginning, I don't have to worry about such things in the first place. But it's an interesting question. The field is actually moving in this direction to ask the question, what's happening when I really do this on a quantum optic single photon level? Okay, so we were asking ourselves, can we observe this also in a laser? Why? Because a laser is a prototypical non-Hermitian system. It has gain because it's pumped. And here at the LKB, it's the right question to ask about pumping and how you can use pumping of a laser to observe an exceptional point. And the laser, of course, also has loss. Not only the bulk losses that you have in a laser, but also the emission losses because it emits light. So in some sense, a laser is a non-Hermitian system already. Can we observe an exceptional point also in a laser? And how would we do it? Not by changing the geometry in a complicated way, but maybe just by applying pump in a certain way. Can we steer a laser to an exceptional point? So this is the question we wanted to ask. And it turns out that the answer we find is related to this plot that I show here. Okay, so what was our starting point? Let's go back to this pitchfork diagram that I already showed before. If you look at this, and I was plotting the imaginary part and the real part of two eigenvalues, then this line here, where the imaginary part is 0, in a laser would be the line where the laser starts emitting. So it's the laser threshold. Because if your eigenvalues have a positive imaginary part, in time they will be exponentially blown up. But of course, the nonlinear effects in the laser will make sure that this doesn't happen. But at least if an eigenvalue is above this line, then a laser is lasing. If it's below the line, then you just have a resonance. So meaning that if we could translate such a diagram into laser physics, then we should see an exceptional point. And what you would have to do is, for example, take a two-section laser. So two, for example, quantum cascade rich lasers that I studied also here at the LKB a lot. And let's start with the case where I pump one of them. One of them has gain, the other one has loss. Then I would start with my eigenvalues, one up here and one down there, meaning if I pump hard enough, this PT symmetric laser would laze on this eigenvalue. And now the interesting thing happens. If I now apply pump to the second part of this two-section laser, and I increase the pump, then what will happen is the following. The eigenvalue that you see here, when increasing the pump, will first go down. Then there's no lasing. But then when it goes through the exceptional point, two eigenvalues will move up. And one of them, or even two of them, will start lasing again. And this is related to what I was showing here, because here I told you adding loss will first lead to less transmission and then to more. And in the laser, what we would expect is adding gain to this section. Although you add gain, the laser first turns off, it moves down. But if you add even more gain, then it goes back up again. And this is a robust effect in the sense that even if the two-section lasers are not exactly the same, but slightly detuned, then you will get a similar behavior, but instead of going directly to the exceptional point, you just have an avoided crossing in the complex plane here. Okay, so when we wanted to observe such a feature, we asked ourselves what would be sort of a good laser to look at. And a natural choice was the photonic molecule lasers based on QCL technology, fabricated in the lab of Gottfried Strasser and Charlie Unterreiner, which is actually the group that Gerald Bastard is visiting every year. They already fabricated two coupled of those terahertz emitting lasers with each other. And we studied whether by applying a pump to those two different lasers in a certain way, we could steer this laser to an exceptional point. So the strategy is here the same. You first pump one, and then you increase the pump in the other one here, and then you see what happens. So we solved laser equations to find out what's going on. And in the laser equations, and I don't have time to go into the details, but we saw that in the lasing equations, we also saw the structure, the Riemann sheet structure associated with an exceptional point. And then, of course, we wanted to know what's the signature in the emitted intensity. as a function of this pumping scheme. So we first pumped one laser. It emitted with a given intensity at a given pump strength in actually two modes that live only in this one resonator. And then by increasing the pump in the second resonator, naively you would expect that the intensity goes up because you provide more gain to the system. But due to the exceptional point, the opposite happens. You increase the gain here, and the laser first shuts off and only later comes back up again. And this is because in the region where the laser turns off, you have an exceptional point. So this was a prediction that we put forward in 2012. And then together with the experimentalists in Vienna, we tried to see this also in the experiment. Here are the results of a 3D calculation of such a 2D coupled photonic molecule laser as a function of pump in one and in the other disk. And you see that if you first pump one disk and then you increase the second disk, then the color which shows the emitted intensity, emitted intensity indeed goes down and then back up again. And since this is a symmetric system, you also see it in that way. So this is something that we expected to see in the experiment. And this is actually the experimental plot, where indeed they see the same behavior, that while you increase the pump, actually your laser first turns off or has a reduced intensity and then goes back up again. To be really sure that this is an exceptional point and not something else, because in QCLs many different things can happen, we asked the question, what would be an additional test to be sure that this is an exceptional point? Well, I showed you this pitchfork diagram before, and if the real part of the frequency is really the lasing frequency itself, then when I go through this trajectory, the laser turns off at one frequency, but when it comes back either at this frequency or at this frequency, but there should be a frequency shift. And so we measured, the experimentalists measured sort of the spectrum along this line, and indeed they saw that the laser which lased at this frequency then turned off. When it came back, it had a slight frequency shift between those two lasing lines. And of course, since this is a symmetric system, you'd also see it if you pump the laser in a different way. In this sense, our original prediction was nicely confirmed, and we could sort of show that by pumping a laser in a certain way, you could actually steer it to an exceptional point. That's actually not quite true, what I just said, because the sad thing about this experiment is the exceptional point occurs in a region where the laser doesn't even laze. So it's sort of a downside of this. So how could we see that even in the experiment that there's really an exceptional point there? This is something that we discussed with a team from Washington University in St. Louis. And they have a very clever coupled resonator setup where they have two microtoroids that they couple to waveguides to the left and right. The coupling between the resonators is done by evanescent mode coupling here. And what's very clever about their setup is the following. They can put one of those microtoroids on one chip and the other toroid on another chip. The black region here in the middle is sort of the air gap in between them. And why is this good to have? Well, it's good to have because this is an experiment that's happening in the optical. So if those resonators don't have the same frequency, then you have a problem to get to the exceptional point. But if those microtoroids are placed on different substrates, you can just heat one substrate, and thereby the resonator expands a little bit, and you can tune the resonance frequency. First of all, you can tune the coupling between them by a positioning stage. And the third thing you can tune is the loss of one of the resonators. What they did is just they used a chromium-coated needle, which they brought in the vicinity of this one resonator. And the more overlap this optical mode has with the chromium tip, the larger the loss will be in this one resonator. So in this way, they could tune the coupling strength, the resonance frequency, and the amount of loss in the resonator. And thirdly, and that's now the important feature, they can not only operate this as a Raman laser and see lasing, but they can also study this whole system just as a passive scattering problem, meaning they send light at the telecom wavelength through one waveguide and then just measure how much is transmitted through this port or through that port. And if they do such a transmission measurement as a function of the loss, so how close they placed the tip to this resonator, they first would see split resonances in the transmission. And then those split resonances, when increasing the loss in the resonance, would evolve into one resonance that would then get sharper. And if you, from those resonances, you would extract the resonance position and the resonance width by fitting procedure, well, then they could map out nicely this pitchfork diagram that I was talking about earlier, where they could really show that, those resonances approach the exceptional point, and then you have this mode splitting and so on. And then they could use the same system, operate it as a Raman laser, and have a sort of a complementary insight on both the passive scattering behavior and the lasing behavior of this coupled system. And indeed, as a Raman laser, they saw that here's the drive. This is the real lasing action. And you see when they increase the loss, first the lasing would go down. So from here to here, the laser would be killed by the loss. But if you increase the loss even further, lasing comes back again. So in some sense, what you would see here is loss-induced lasing. You add more loss, and the laser goes above threshold. And this is also seen by the threshold curves. The laser lines, the threshold would first be shifted up by the loss, and then would come back. And in this way, we could also then map sort of the passive with the active behavior of this whole system. Okay, so this was something where we could demonstrate that exceptional points exist in lasers. You can actually see them in this way, but other people also thought about, can you actually do something useful with them? And here are two experiments that appeared in Nature, I think 2 years later, or 1 year, not sure now. One by the Berkeley group and one from Creole in Florida. They fabricated lasers that had a PT symmetry or almost PT symmetry. In this one case, they showed that if you add to a ring structure, which has several modes lasing, a second ring that doesn't have gain like the first one, but has gain and loss paired with each other, then you could use this as a nice way to achieve single mode emission, because sort of only the one mode that goes through this exceptional point will be above lasing, and all the other ones don't have this splitting. That's why only one mode lases. So they achieved single mode lasing based on parity symmetry. And those people in Berkeley, they had a ring laser, patterning it with chromium to get the loss, and then pumping it optically from the top, so they had gain, loss, basically like a DFB grading, and they said they also got a single mode emission from the structure. Okay, what else can you do with exceptional points? Something that I find particularly attractive is that exceptional points do not only have this feature that the eigenvalues coincide, but also the eigenvectors are the same. What would that mean now for a laser? Well, the interesting thing is that if you have a whispering gallery mode cavity, like a ring or like a microtoroid, typically you would expect that you have two degenerate modes, like one clockwise propagating, one counterclockwise propagating. And they should be degenerate, such that you can also choose them as two standing waves in whatever basis you choose. But if you now sort of modify this resonator by two parameters, and for example, you bring two scatterers close to it of different size and different distance to the resonators, then you can bring actually those two modes that are in your resonator to an exceptional point. But since at the exceptional point only one eigenvector exists, which one is it now? Is it the clockwise or the counterclockwise? So this is a way to achieve a chiral mode that has a chirality, so a determined sense of direction, that for one exceptional point is like this, and another exceptional point will be like that. So in this sense, by steering a system to an exceptional point, you can actually choose or engineer the way in which a mode runs around in your resonator, which I think is a very, very beautiful feature. And you would think this cannot be because it breaks time reversal symmetry. But of course, it does not break time reversal symmetry for the whole universe. But since you have an outcoupling sort of in your subsystem that's described by the non-Hermitian Hamiltonian, this is possible. Okay, so again with the group from St. Louis and with Jan Wirsig from Germany, we tried to see this in the experiment, and by measuring the transmission through those two waveguides and 4 ports, you can actually deduce from the transmission and reflection amplitudes what the corresponding chirality of modes inside the resonator is. And we could show that by going from one exceptional point to another one, the chirality could be actually dramatically changed from very clockwise to very counterclockwise. And if again you run this thing as a laser, this laser would then sort of be a ring laser emitting on such a mode or on such a mode, depending on actually on which exceptional point or near which exceptional point you are. Now this is sort of a proof of principle demonstration, but very quickly, again, Lian Feng and his team, who was in Berkeley before and then moved to Buffalo, they thought about, can we use this for something? And they came up with the idea that by steering such a patterned laser to an exceptional point and making sure that you have gratings that let this laser emit to the top, they could actually engineer a laser that has a vortex laser beam, meaning laser light that has a well-defined angular momentum. Of course, the angular momentum cannot then be changed in situ, but for one structure, they could show that this would emit sort of a vortex with an angular momentum that's determined by the periods of this grading and so on. Okay, so it's sort of a new way of designing such modes in such systems. There are also many other works that I don't have time to talk about, many of them in high-profile journals. So you see this is a very fashionable topic at the moment. And there are still many interesting topics to explore. For example, traditional laser theory tells you that if modes are non-orthogonal, then the so-called Petermann factor would increase, meaning that the laser line should be broadened. For example, it's still an open question. What happens at an exceptional point where the Petermann factor diverges? How broad is the laser line at an exceptional point? Interesting question that's not yet explored. Okay, to keep the story short, there are many things that are being done and many more open questions to be explored, but all of the things that you see here are based on actually the eigenvalue and eigenvector structure of exceptional points. But something that was not explored in these works, but something I want to talk about in the rest of the talk, is whether we cannot also use or make use of the topological structure of the eigenvalue surfaces in the vicinity of the exceptional point. You see those Riemann sheets, they have a very specific topology that is always the same for an exceptional point involving only 2 modes. There are also higher order exceptional points, by the way, where this topology can become more complicated. But for an EP2, this structure always looks like that. And so the question is, can we sort of observe in physics or through an experiment sort of the topology of those Riemann sheets? And there have been already works in the past. And here again, I take the pictures from this reference. People have pointed out that, let's say you have an eigenvector at one specific parameter position of your system that is on this surface, for example, lives at point A. in this coupled photonic molecule, this would correspond, for example, to such a mode. And then, what would happen if I change one parameter, like the radius of one disk in the system, and move this mode down here? Well, then I would follow on this sheet the eigenvalues like this. In the imaginary part, I would also follow it. But since I have an anti-crossing here, I would stay on this sheet like this, and here I would go through this crossing like that. If I now continue this game and move my parameters such that I actually encircle the exceptional point, so I now change the second parameter, then the third, and then come back, then I'm in the absurd situation that at point E up here, I'm actually at the same parameter point as at point A, but the eigenvector up here corresponding to this eigenstate is a different one than the one I started out from because of this topology. I move up, so to speak, to the other Riemann sheet. And only if I encircle the exceptional point the second time, I go back to my original starting point. Which is also not true, because I get a geometric phase of pi. So to be really back, I would have to encircle the exceptional 4 times to go back to my starting point. And of course, the big question is, can we sort of observe this abstract mathematical physics result in a real world experiment, and what would it mean, or how would we have to do it? And there were people looking into this already 15 years ago. This is the group of Achim Richter at Darmstadt with the support of Wolf-Dieter Heiss, who is a pioneer of those exceptional points. And what they did is, again, use a system of 2 coupled resonators, now in the microwave domain of macroscopic size. And in this microwave resonator, which has sort of it's split into 2 parts, and modes that live here can actually penetrate from one resonator to the other one through the slit. So this slit width S determines the coupling strength. And they introduced another bumper here that could move the mode a little bit, called delta. And then to observe this, this effect of encircling an exceptional point, what they did was they inserted an antenna into the resonator, then scanned the frequency and looked at what the resonances look like, then deduced what the corresponding states look like, did the measurement for one specific parameter value of delta and S, so for this and that, and they concluded the mode looks like this. Then they changed the parameter delta a little bit, did again a measurement, changed it again, and they knew where the exceptional point is, and then they did this thing, connected the dots, and then they found if they do it according to the prescription shown here, they would indeed go from this mode to that mode, although they are now at the same parameter value. So this was sort of viewed as a verification of this exceptional point encircling idea. And also recently, by the way, a group from Australia implemented the same protocol in a exciton-polariton condensate. But, so there's one small but there. What they did was actually several experiments consecutively, connecting the results of the experiments a posteriori. And they sort of, they did this assuming that if you could actually really create a state in a system, and then while the state lives or while it decays or gets amplified or whatever, you continuously change the system parameters, that you would then get the same results as here. Why? Because they said if you just change the parameters slowly enough, then you could apply the adiabatic theorem and say, if I do this slowly enough, I will always follow in my time evolution the instantaneous eigenstates on my eigenvalue sheets, and then I would get this result. But there's something incorrect in this reasoning. And the reasoning is that You need gain and loss to get an exceptional point in the first place. Okay. But if you have a non-Hermitian matrix with gain and loss, the adiabatic theorem doesn't work anymore. So this means that even if you change this infinitely or very, very slowly, well, first of all, if you do it too slowly, the state will decay anyway. There's nothing left experimentally, it's gone, because this is a lossy system. But even if you do it slowly and you still get a final signal, due to the fact that gain and loss are there, you get corrections that are actually not small corrections, but mathematicians would say these are singularly perturbed problems. So by adding gain and loss, you get a different result. And this was pointed out by people like Nimrod Moiseyev, Michael Berry, and we also studied this problem theoretically in Vienna with Peter Raubel. And so the statement is, if you are on such a Riemann sheet around an exceptional point, and I just show here the real part of two eigenvalues, then there are trajectories where you indeed, and this is now a full-time evolution, so we prepare an eigenstate at time 0 that uniquely lives on this sheet, and then while the state lives, we follow it dynamically and see where it goes. And the statement is, there are movements that are following the adiabatic principle, but if you are adiabatic by encircling the exceptional point in one way, then you can strictly prove if you start on the same initial starting point, but then you encircle the exceptional point the other way, the adiabatic theorem will not hold anymore, and you will get additional contributions which make that this final point of this trajectory is not here on the bottom, but there will be a jump in between the sheets and you will end up on the other sheet. So what's the reason for this? The simple physical explanation is the following. Let's imagine you are on this Riemann sheet and you enter the loss part. So you're in an eigenstate that's very, very lossy. So it's damped. But due to the fact that you move the parameters, a little bit of your contribution will also populate the gain part, which is exponentially amplified. And this amplification, after some time, will lead to the fact that your trajectory doesn't stay on the loss sheet, but it will make a non-adiabatic jump to the gain sheet. And this is what you see here. So at first, one thinks, okay, that's somewhat sad that non-adiabaticity destroys this nice picture. But as it turns out, due to the fact that you can prove that if you're adiabatic in one direction, you're non-adiabatic in the other one can actually deduce a very nice result that was first pointed out, I think, in this paper, which is that if you sum up, if you look at all the different directions, so you start on the top and on the bottom and you encircle clockwise or counterclockwise, then you can show that no matter where your starting point is, the encircling direction of the exceptional point alone determines where you end up with. Okay, that's a complicated statement. I try to illustrate it. So here I start on the top and I encircle the exceptional point in a clockwise way. Here I start on the bottom and I also encircle it in a clockwise way, and you see that the end point is always the same. So meaning that if I encircle clockwise, I end up there. Here's the opposite. I start on the bottom, I encircle counterclockwise, I end up on the top. And also here, I end up on the top, independent of where I started from. And just the direction of encirclement determines where I end up. Meaning that I sort of get, again, a certain chirality, which tells me that I get a behavior where, independent of where I start from, I will always end up in the same state when I just encircle the exceptional point in a certain direction. And this triggered us to think whether one couldn't use this in some sense. Let's assume one could use this by mapping the time propagation onto a propagation in space through a waveguide. And let's assume this waveguide has two modes. If I can design this waveguide in such a way that during propagation I encircle an exceptional point, this would mean that independent of in which arbitrary linear combination of modes I come in here at the left, I will always scatter into the second mode. And if in this waveguide going from left to right means I encircle the exception point in such a way, then going from right to left means I encircle it in the other way. So, but if this means that I end up in the other state, it would mean that if I come in an arbitrary linear combination of first and second mode, then going this way through the waveguide, I always scatter in the first mode. So I would have now an asymmetric chiral sort of waveguide design that, I don't know, could be useful for designing new types of photonic structures. And the way we worked on this project was to say, let's work with waveguides that have sort of a boundary modulation, because this is something we have some experience with, together with the group of Ulrich Kuhl at Nice, who fabricate waveguides of certain design. And we decided, let's try to get this to work with surface modulated waveguides. And the trick is, of course, to design the surface profile and the loss inside those waveguides in such a way that one actually encircles an exceptional point with those two modes when propagating through the system. And here the two parameters that you change along the way are actually the boundary modulation, so the amplitude of the boundary modulation, and sort of a detuning in the frequency of those modulations. And if you change those continuously going around an exceptional point, then you effectively have a Hamiltonian where, as a function of propagation direction, you do this encircling of an exceptional point. Okay, I spare you the technical details. Here are some numerical results. For a waveguide that has such a modulation, the blue is actually here the amount of loss that you have. So we start with a straight waveguide that has no loss. We crank up the loss and then it goes back. And the modulation here follows this encircling of an exceptional point. And now you see the results. We come in mode 1, and we end up in mode 1. We come in mode 2, and we also end up in mode 1. Of course, the dirty little secret is the intensity that comes out here is very, 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 very low. So that's the price you pay for having loss in this waveguide. On the other hand, if we come in from the right, we come in mode 1, end up in mode 2. And also when we come in mode 2, we end up in mode 2. And you see, even if you look very carefully, this transition is adiabatic. The wave function or the electric field looks very smooth. So this is an adiabatic encircling. Here you see that there is something happening, and this would be the non-adiabatic jump. But of course, since the efficiency of this device is very bad, and it's also very long and bulky, actually the size of it would be larger than the lab space that they have in Nice. So we thought hard about, can we improve this? And here is the improved design, where the loss is not uniformly distributed now in the waveguide, but along a certain carefully designed pattern. And also sort of the wiggles in the boundary are very reduced. And we get here the same behavior that independent of which mode you come in, you end up in mode 1. And when you come in from the other side, you end up in mode 2. So with this design, we contacted our friends in Nice and asked them, can you do this in your workshop? And this is the structure that they built. This is a sort of microwave waveguide that fits on this table. Here are absorbers that mimic infinite leads. Here is the boundary modulation. This is the top plate that can be screwed on top. And here in the middle, you have an absorber that's made of a black foam that absorbs this. And indeed, when they did the measurement with antennas here and antennas here, they found that they get this behavior. So this is the transmission intensity as a function of frequency. And you see that T21, the green curve, means I come in mode 2 and I end up in mode 1. And this transmission is much higher than if I come from mode 2 to mode 2. So meaning, if I come in mode 2, I primarily scatter into mode 1, because this green curve is much larger than the red curve. If I come in mode 1, I also scatter primarily into mode 1, because the blue curve is much larger than the gray curve, which is the transmission from mode 1 into mode 2. If I come in from the other side, these are the dotted lines, then T prime 1, 2 is much larger than T prime 1, 1. So I scatter primarily into mode 2, and also the red curve is much larger than the gray curve. What worried us a little bit is that transmission from left to right is not exactly the same as from right to left. So this would indicate that we break Lorentz reciprocity, which the encircling of the exceptional point does not. But the absorber, we figured out later, contains some elements that have a little bit of a magnetic stuff in there, so that's why you have a little bit of breaking of reciprocity there. But this is not sort of part of the design principle. Okay, so this came out just last year. And when we submitted this paper, we also had a referee asking us, how can you actually be sure that, that in this waveguide you really encircle an exceptional point and don't do anything else? So to answer this question wasn't easy, but we asked ourselves, can't we just say, okay, if this is our waveguide that we have, and we continuously change the parameters from entrance to exit, meaning that while doing this, we encircle the exceptional point. What people did previously was not such a continuous variation, but they did sort of one measurement here, one here, one here, and one here. So we said, okay, let's do the same. Let's, for example, at position 3, continuously, periodically continue this waveguide, and then look at waveguide measurements where one waveguide looks like this, corresponding to this position. One waveguide looks like this, and then we did individual measurements for each one of those waveguides, corresponding to this stroboscopic encircling. And if we did that, we really found that one can actually nicely see this previously shown adiabatic result, where you get sort of a jump from one Riemann sheet to the other, and in this way confirm that also if we do things the old way, let's say, we get results that are consistent. Okay, there have also been other proposals for waveguide designs. Meanwhile, people also looked at the problem of a waveguide that contains nonlinearities. In this paper, it was shown that you could get broadband non-reciprocity if you add nonlinearity to the system. In an experiment at Yale that appeared in the same issue as ours, they did actually an optomechanical experiment where they fully dynamically, by tuning a laser from the outside, they could steer their membrane in a cavity around an exceptional point, mapping out this Riemann sheet structure, and also see this switching behavior. Other people from Florida and from MIT, they proposed sort of a waveguide which they pumped in the middle to achieve what they call an omnipolarizer, meaning independent of light polarization of the incoming beam, due to the fact that while propagating through the system you encircle an exceptional point, you always end up at the end in a certain polarization state, and if you come in through the other way, you end up in the other polarization state. Okay, I think I'm anyway running out of time. Let me briefly summarize. In the first part of my talk, I was speaking about lasers and how exceptional points lead to a loss-induced suppression and revival of lasing. We also observed chiral resonator modes, and in the end, I was talking about topological aspects or topological photonics with exceptional points, resulting, for example, in asymmetric mode switching in waveguides, polarizers, and in optomechanics. A big question is, and this is something where I think the field is moving to, what would be sort of the interesting consequence of an exceptional point in a truly quantum optical setup, which is related to a question that was asked. And we are also moving in this direction. Maybe if somebody here is interested in this topic, I'm still here today, and in the morning tomorrow, I'd be happy to discuss this further. Now, okay, the most important part, I want to acknowledge help from many collaborators. Matthias Lierzer, my grad student, was the main guy on the laser things, but we also collaborated with people from Princeton, Japan, Yale, Carl Bender, who invented this PT symmetry. These were the experimentalists involved in this quantum cascade laser paper that are very well known to some of you. The team in St. Louis, Shahin Özdemir, Bo Peng, and Alan Yang. And finally, the people involved in the encircling of the exceptional point. Jörg Doppler is my former grad student, Alexei Malibayev in Brazil. The team in Nice who did the experiment, Peter Raubel and his former graduate student, and Nimrod Moiseev, who worked in this field for a long time. Okay, last but not least, I also want to advertise our review with Sylvain that we worked on for many, many years, and which finally got out a few months ago on a different topic, mesoscopic scattering meets wave control. So if this is something that you may be interested in, let me know. I'd be also happy to discuss it. And then, last but not least, I want to acknowledge my funding and you for your attention. Thank you.
Thank you very much, Stefan. It is time for questions.
Maybe to get more intuition, because this asymmetric circling, is it true to say this is a hysteresis? It's like a magnetic hysteresis? Or it's more rich?
No.
No?
I think hysteresis you can only get if you have a nonlinear system, right? Here this is all linear.
But you do have to play with gain and loss.
Yes, but the gain value here was always below some lasing threshold where nonlinearity would then kick in.
Okay.
But sort of, this is still linear. Only if you crank up the, in the laser studies, the nonlinearity comes in, but it just stabilizes the laser modes, but sort of the exceptional point was sort of below the lasing threshold, where it's still completely linear. So it's not a hysteresis effect.
Okay.
Did you actually go to the exceptional point, or is there some effective level repulsion which brings you away and projection from higher dimensional space? No, you can actually go to the exceptional point. There's nothing that prevents you from that. And I can tell you we're at the moment working on trying to understand what happens actually when you go to the exceptional point. Let me mention one interesting project that people have been pursuing that may be interesting for sensing applications. Let's assume at the exceptional point you have this square root behavior of your eigenvalues. And let's assume you want to, for example, use your cavity to detect particles. People do this to detect very small particles in a liquid. And they detect them typically by seeing a resonance splitting when they shine light through a side-coupled waveguide. And you can show that if you use normal modes that are not at an exceptional point, then sort of the sensitivity of this detector means that the closer the particle comes to the resonator, the more you will get a splitting, but there's a linear behavior. If you are at the exceptional point, you can be more efficient because at the exceptional point you have a square root behavior, meaning that if you just perturb your modes a little bit, you will already get a higher level repulsion in the change than if you're not at the exceptional point. So in this sense, being at the exceptional point right there means that you will be very sensitive to external perturbations. But of course, it's a detector that only works once. Once the particle is there and it shifts you away from the exceptional point, you would have to recalibrate this and then do another experiment. But people think about what can you do when you're right at the exceptional point.
So away from linear physics, you could think that you start with a system that has some degeneracy somewhere.
Yeah.
Then you engineer drive and dissipation or loss and
Yes.
gain, and you could transform this point into an exceptional point, right? Or is it some? Is it this kind of?
Good question. So the typical scenario is that, for example, you go to what is called a diabolic point, which would be an accidental degeneracy in a Hermitian system. And if you then add to this diabolic point, which by the way is called diabolic because of this diabolo thing, if you then add gain and loss, typically this diabolic point will split into two exceptional points, one having this chirality, one having that chirality. Yeah. Because, you know, when you have exceptional points in a system and you remove gain and loss, they have to disappear. And what happens is the two seem to sort of always merge, cancel each other, and then the effect is gone.
I just imagine there's some analogy with, exceptional point in fluid dynamics, and
Yeah.
because in some fluid system.
Yeah, yeah.
And, well, it's a question. I mean, can you
Yeah.
figure out some situation where you will have something similar?
Typically, my experience is that if you have some kind of system that's described by a Hermitian matrix or operator, and it can be Navier-Stokes or whatever, and you then add sort of dissipative or gain terms, you will always see
So
exceptional
we have
points.
plenty of them.
I'm sure. So there are also plenty of
Especially
them
in
there.
turbulence, yes.
Yeah, so there are plenty of them there, and the question is, okay, how can you steer your system there, and what would be a hallmark of seeing it? Yeah, but I'm very confident that, I mean, those exceptional points are everywhere in non-Hermitian physics.
Thank you very much. Thank you again, Stéphane.